All right, so today we're going to be talking a little bit about molecular orbital theory and some molecular orbital diagrams. So, things to know before we start. A molecular orbital diagram, which we will look at in just a second, which I think you have seen in a previous video, is a representation of the bonding orbitals that are formed to hold bonding electrons. So, these are slightly different from your atomic orbitals, but only in that they are used for bonding and so will overlap between two elements. There are both sigma and pi, as well as sigma star and pi star orbitals on a molecular orbital diagram. Sigma and pi are the bonding orbitals, and sigma and pi star are what we called antibonding orbitals. So if you have the same number of electrons in antibonding as you do in bonding, no bond will occur. They essentially cancel each other out. And then we've got this thing called bond order, which can help to determine the type of bond, right? Single, double, or triple, that is going to occur between two elements in a molecule. And how you figure this out is you take the number of bonding electrons, subtract from that the number of anti-bonding electrons, and then divide that number by 2. So let's take a look at a bonding orbital here, or a molecular orbital diagram. So in this, all right, you might notice that 1s is not represented. A lot of times you will not have 1s represented. It's going to look the same as 2s, right? So you would have your two lines here in the middle, your sigma and your sigma star. Now, why we don't represent these most of the time is that unless you are dealing with hydrogen and hydrogen only, all of this will be filled up, right? You will have your 2 electrons from your 1s and your 2 electrons from your other 1s, and that makes 4 electrons, and you will just fill all those up in here, right? Because these work exactly like any other orbital. They hold 2 electrons, and that's the number that they hold. So that's why we don't see the 1s on here. But getting into this, if, let's say, we have 2 oxygens here. Now, oxygen, if we remember how many electrons it has 6 valence electrons. So for each oxygen, we'll put in our 1, 2, 3, 4, 5, 6 electrons that each oxygen has in its 2s and 2p. 1, 2, 3, 4, 5, and 6. Okay. And then all we do is we start filling up the molecular orbital diagram in the middle. And so because we have 2 here, that's 4. We put 1, 2, 3, 4. And up here we have 4 and 4 for 8. So we make 1, 2, 3, 4, 5, 6, 7, and 8. So there we have all of our electrons accounted for, and that's how we fill in our molecular orbital diagram. Now if we wanted to do bond order, we want to figure out our bond order. We would count up the number of bonding electrons here. So we've got 2, 4, 6, 8. So we have 8 bonding electrons minus our 2, 4 antibonding electrons, and divide that number by 2. Now, 8 minus 4 is 4, divided by 2 is 2, which means we should have a double bond between oxygen if it's O2, and if we draw a Lewis diagram of this, as it turns out, this is what it would look like. It would have a double bond. So it all works. That's really all there is to molecular orbital diagrams. That's it. So, I mean, I guess if we wanted to look at, let's say, argon, right? We know that argon, everything in 2s is going to be filled, right? Or maybe that's neon. Maybe I'm actually thinking of neon. It's probably actually neon. Maybe I'll change that. Neon. So when we go to fill these up, right, we've got our 4 electrons here coming from 2 on this side, 2 on this side, but on this time we have 6 on each side, right? So do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So everything is filled up, right? So if we look at our bond order here, we have 2, 4, 6, 8 electrons and 2, 4, 6, 8 anti-bonding electrons. And 8 minus 8 is 0, divided by 2 is also 0, which means we have a bond order of 0, which means this is not going to form a bond. So when we get to describing the orbitals that go into a molecule, those things in the center, the sigma and pi's, we talk about them as being hybridized. So when forming molecular bonds, atoms will create hybrid orbitals so that the bonding electrons in a molecule are held in orbitals with roughly equivalent energy, right? So they want them to be similarly energetic so that when you are forming bonds around a molecule, they all have more or less the same energy, so they form a nice geometric pattern instead of being lopsided. Like when we talk about molecular geometry, right? We've got these nice geometric patterns. The second point, like with electron domains, any bond, right, that means single, double, or triple, contains one hybrid orbital. In this case, lone pairs also occupy a hybrid orbital. Double and triple bonds contain non-hybrid or unhybridized pi interactions. So we will talk about this. The pictures in your book are good. You should take a look at them because me drawing them is, I think, just going to be confusing, but your book does a good job. So, creating hybrids, all right, how we create these hybrid orbitals. So for creating orbitals, atoms use both their s and p orbitals to create hybrids. So the number of hybrid orbitals in a molecule is always equal to the number of bonds, single, double, or triple, and are named based on the number and type of orbital used. So how this works, right? So if we have CH4, right, we know that the Lewis dot structure looks like this. So it has 4 single bonds, which means it needs 4 hybrid orbitals. And we know that carbon has some s and p orbitals available. So if we remember that s has 1 orbital and p has 3 orbitals, it means that carbon has 4 orbitals available. And if we count on our fingers here, right, and I'm about to draw my hand, look at that hand. So if we count on our fingers the number of bonds, 1, 2, 3, 4, we will need 4 hybridized orbitals. And if we count here, we have 1, 2, 3, 4. And so we have an S and 3 P's, which we say the hybridization of this carbon is sp3. That is how we do hybrid orbitals. So like in the case of HCN, hydrocyanic acid, we have our H, our C, and our N. And then again, right, if we look at the hybridization on carbon, we have the same number of orbitals again, right? And if we count on our hand here, an even better hand this time, we have 2 bonds, right, that need hybrid orbitals. So we count 1, 2. And here we count 1, 2. So in this case, the hybridization of carbon is just sp, because we've only used our s and one of our p's. Hopefully this is starting to make sense. That is the way hybridization is talked about. We talk about sp, sp2, sp3, and that's about it. So, how this all works. Now, if you see this flashing disclaimer here, my drawings are going to be bad. The pictures in your book are good, so go read those sections. I will attempt to draw a little bit of this, but as I said, I would really recommend going to look at your book. So we have our s orbital and our p orbital, right? They look kind of like this with our nucleus in the center. So when these hybridize, right, because these are not of equal energy, and so what happens when they hybridize, they make this new shape that's kind of like this. It's this weird S and P hybrid, and you get a couple of these. And if we have something, right, like I don't know, hydrogen, right? Well, we've got one single bond between the two. I guess that's a bad example because they only have the one orbital. But let's say just carbon-carbon, right? Carbon to carbon, single bond. It's got some other stuff over here. It doesn't really matter. So each of the carbons is going to form some bond or some orbital that looks like this, right? So what happens is we have our carbon atoms with these hybrid orbitals that overlap between them, right? So we've got some overlap where there's electrons that are shared. And that's how a single bond works. We've got these hybrid orbitals that are essentially overlapping end to end. We're sharing electrons. Now, if we had a carbon-carbon double bond, right, we would still have those overlapping hybrid orbitals, but we would have these unhybridized orbitals, right, that are like our p orbitals, right? We have unhybridized p orbitals. And what happens is these kind of form this bridge above and below our hybrid orbital, right? And this is our double bond bridge. And that is what happens, right? So these are above and below the carbon, and the hybrid orbital is in the middle, right? So that's what happens if we have a double bond. Now here's where the drawing is going to get really crazy, because if we have a carbon-carbon triple bond, right? We've still got carbon, it's still got these hybrid orbitals, right? Hybrid orbitals. And then we still have, let me try this. I'm going to change the color. We're getting fancy, right? And we've got our p orbitals that are above and below that have this interaction here. But then for the triple bond, right, what happens is we actually have another p orbital that's unhybridized, and it makes these interactions next to the carbons, right? So you have your hybrid in the middle. Oops, that's red. So hybrid. And then you have your green that are pi interactions for your double bond. But then you've also got another set of pi orbitals that form the triple. Right? And so you've got all these interactions going on between these two carbon atoms, between hybridized and unhybridized orbitals. And that is how this all works. So like I said, I'm sure my drawings were a little confusing. So go check out those sections in the textbook. The drawings are much better. Hopefully they will make more sense. Okay, so now I know we've talked about this a little bit in class, but here it is again. Paramagnetic and diamagnetic. So just like looking at individual elements when we look at their orbital notation, we can see when things have unpaired electrons. The same is true with molecular orbital diagrams. So paramagnetic, when a substance has unpaired electrons in its molecular or atomic orbitals, causing it to be attracted to a magnetic field. Diamagnetic, on the other hand, substance with no unpaired electrons, causing it to be repelled by a magnetic field. Now, if we remember oxygen, O2, from our example earlier in this video, it had unpaired electrons in one of its anti-bonding orbitals, making it paramagnetic, which means that oxygen itself as a molecule will be attracted to a magnetic field, and maybe we can watch a video of some liquid oxygen getting stuck between the poles of a magnet, because that's always fun. So kind of the takeaways here, things to remember: atoms will form one hybrid orbital for each bond and one hybrid orbital for each lone pair. The bond order can tell you what type of bond will form and is found by looking at both the number of bonding and anti-bonding electrons. All right, that's going to do it for the molecular orbitals. I will see you in class.